At North Central College, undergraduate research can take students far beyond the classroom, even into one of the most ambitious physics experiments in the world. This is episode 14 of 1861, the North Central College podcast. And our guest is Dr. Paul Bloom, professor of physics at North Central. Dr. Bloom has been part of the international Muon G2 collaboration at Fermilab, an award-winning physics experiment that has also involved some of Dr. Bloom's students. Today, we'll talk with Dr. Bloom about the questions at the center of this work. What exactly is a muon? Why do physicists care how it behaves? What does it mean when an experiment points toward the possibility of something beyond what science already knows? And how does a place like North Central give undergraduate students a meaningful role in research that's happening on a global stage? With that, we say hello and welcome to Dr. Paul Bloom. Paul, thank you for your time today.
Well, thank you, Jim. I'm very happy to be here.
Welcome to the podcast. Paul, we have a lot to talk about today, but let's start by giving listeners an opportunity to learn a little bit more about who you are. And so, what first drew you to physics?
Just the idea that we could know how things work, whether it's just stuff around your house or the world around us. And in the end, that's what physics really is about. It's understanding the principles and the principles that tell us how the universe around us works. And it's not just about ideas, it's also about being, because it's science, it's predictive, right? The idea that I can build a model, I can use mathematics and predict, if I do this, what should happen? Or if I observe such a thing happening, what is going to happen next? It's a statement about the rationality of the universe, that it is predictable, even if that prediction is chaotic, which it certainly can be at times.
Yeah.
But the fact that we have a methodology for asking questions about how the universe works. And that's really what science is about. The whole of the scientific endeavor is about this way that we humans have figured out to ask questions about the natural world. How does this work? Why is something happening? If I do this, what will happen? And it's something that as a society and a civilization, we've benefited enormously from, whether it's technology or learning, figuring out how to make good decisions. What should we do next? Well, if we do this, what will happen? And, in terms of our success as a nation, as a people, when we allow science to inform us in terms of what are we going to do, we do well. And we ignore that understanding to our peril.
Yeah, absolutely right. Paul, tell us about your educational journey. Where did you earn degrees? What kind of research did you do?
So I was an undergraduate at a small college in Portland, Oregon, Reed College, 1,200 undergraduates. So roughly 300 students in a year coming in.
Yes.
And very small, traditional liberal arts college. I was a physics major, so I took a lot of physics courses. I took a lot of math courses, but I also took courses across the spectrum, because that kind of broader education is what helps you be a more rounded person. If you study only one thing, you don't understand that there are lots of ways of looking at the world, of thinking about the world. And as a scientist, we need to be able to think critically. We need to be able to communicate, not just to our peers, but to the general public. How do we do that in terms of the words that we say and the things that we write? So all forms of communication, because if you learn something interesting and you don't disseminate that knowledge, it's the if the tree falls in the forest and no one hears it, right? But it's the
That's
same
right.
thing. If you discover something in the laboratory and you don't tell anybody about it, did you actually learn anything, right?
Yeah.
That it's all meant to be part of a broader endeavor of human understanding. So I went to Reed. I majored in physics, and during that time, it's by the way not the reason that I went to that college. I had one of the things that I'm always very happy to tell my students, my advisees, is that I knew exactly what I was going to do when I went to college. I had a plan. And that plan was I was going to get an MD, PhD. I was going to be a biology major. And I knew exactly what I wanted to do. I was going to be a research endocrinologist. And my college advisor said, great, you should probably take physics and get it out of the way. Because, of course, you take physics if you're going to go to med school.
Right.
And I fell in love with it. And from that point on, I was going to be a physicist. And I gained the skills that one acquires as part of a physics curriculum. Eventually, as part of being a senior at Reed, you do a thesis project, an independent project, year-long project. And just having that experience of actually doing research and learning to do something new and to work on my own in a really sort of a long-term, not just doing a homework assignment, but really a big project that really made me think, you know what, grad school, I want to keep doing this. And so, I went to grad school. So I have a BA from Reed College. I went to grad school at the University of California at Davis. And, I did my PhD there, again, graduate level courses, getting into the research project that eventually brought me to actually live in this area. I lived in Naperville for 4 years as a graduate student while I was working at Fermilab on the D0 experiment, on the Tevatron, the big particle collider that was there. But maybe the most important thing I learned in graduate school was not physics. It was looking around and watching what it was like so I had just come out of a 4-year experience where I was in small classes. I knew all my professors and I worked closely with them. Even, I'm taking a history course and I'm not going to be a historian. It didn't mean that I wasn't in talking to my professor and discussing, okay, I read this and I'm going to write this paper. And then I get to a place like Davis, which is a great school, but there are, 20 some thousand undergrads and all kinds of graduate and professional programs. And I looked at the way that undergraduate education was, where in my own experience versus what I saw at Davis. And I realized, I know what I want to do. I want to be involved. Yes, I want to do physics and I want to continue doing physics, but I want to be involved in education, and especially seeing the value that the experience of being at a small college, of being at a liberal arts institution that focuses not just on preparing you to, go into some vocational track, but really teaching you to think critically and broadly, and being closely involved with your professors. Many of my own professors who I made lifelong connections with, well, I wanted to do that. And so seeing how that worked at UC Davis, that was the moment where I said, I want to be a physics professor, but I want to do that at a small college where I can be part of that, of that interaction, of have that experience of working closely with my students. I don't want to be in front of I at one point as a grad student, I TA'd for an introductory physics course where there were so many students enrolled in the course, they didn't even all fit in the lecture hall. So some of them watched the lecture in a different room on a closed circuit TV. And I said, I understand it, but also that is not the experience that I had. It's not the experience I value. I want to be part of doing the thing that is meaningful. And so, yeah, eventually I knew what I wanted to do was I had to finish my degree. And so I did that. I took a master's and then a PhD at Davis. After that, I did 2 postdoctoral research appointments, one for McGill University in Montreal, although for 1 year at the Triumph laboratory in Vancouver, BC, 2 more years at SLAC at the Stanford Linear Accelerator Center. And then I did a second 3-year postdoc for the University of Colorado at Boulder, but again, at Stanford at SLAC, because when you are doing high energy physics, the kind of physics where you want to study what are the fundamental constituents of matter and how do they interact with each other. If you're a researcher, that's where you want to be. You want to be at the laboratory. And so as a postdoc, that's where I was. But always in the back of my head that what I wanted was not sort of the typical track, because the typical track, and you get a graduate degree and then you might do some postdoctoral work, but what you're aiming for is a research position at a large university. And that's sort of the machine. And I knew that wasn't for me, that could I do that? Yes. Do I want to do that? No, because that would not be as meaningful as being involved in sort of the transformation that occurs in students, in these 20-year-olds who are right in the middle of this journey of becoming who they are going to be. And I get to be part of that, which is awesome, right? I mean, that's the best thing. It's the best thing about being involved in undergraduate education. It is the best thing about being at North Central, right? That I'm part of this transformation that so many of my students have made, where they are becoming whoever it is that they're going to be in this world.
You've been at North Central for 20 years now. 20 years. How does that feel?
Well, I was joking with my colleagues when I started here. I thought, boy, I'm going to really connect with these students because I'm the cool young professor. And, I went home and I told my wife about that. And of course, she laughed in my face,
yes,
as true love does.
Yes.
Because, hey, pay attention. You're the age of their, they could be your kids. Not to my knowledge, but
yes, right.
And it's been a transformation of how I think about myself as, what is my role here? That I'm a mentor, I'm a guide, right? That I'm not simply a fount of wisdom where I'm going to tell you how all this stuff works, right? That I'm going to be, your experienced guide as you make your own journey through becoming and through learning, and that's that transformation has I think turned me into a more effective instructor, a more effective mentor. So growing up, it's funny because the thing about North Central is it was never on my radar. I lived in Naperville for 4 years.
Yeah.
And I didn't even know the college was here. And then I go and do postdoctoral work, and I did a visiting teaching position. And so 10 years later, I end up back in the same place, and because here is North Central.
Yeah.
And, it was a fantastic opportunity because not only did I get to do the things that I wanted to do in terms of being involved in undergraduate education, but Fermilab is, stone's throw away.
Yes.
And that meant some really great opportunities in terms of the things that I could do as a scientist. And most importantly, of integrating that work with student education, because one of the things that we really understand about learning to do science is that you have to do it, right?
Yeah.
That we
Yes.
I can teach you things out of a book, I can teach you how to solve problems, I can teach you laboratory skills, but in the end, you don't really know what it means to do science until you try to do science. And that includes successes, it includes the failures, it includes the absolute bewilderment of not understanding something that just
Hmm.
happened,
Hmm.
and having to, to examine your assumptions about, well, here's what I thought I was doing, what was I actually doing? uh,
Mm.
and that process, right, that's the one thing that I think distinguishes students who, especially at small colleges, who are majoring in science but get to actually be involved and engaged. You learn about the doing of science, and especially in a field like physics, where, because so many of the ideas and the topics that students are going to explore as undergraduates, those have been around for a long time. Though you're in a classroom and you're learning something out of a textbook that
Yes.
has been well understood for more than 100 years. And when that happens, you have to understand that what you're encountering is the sanitized version of that process. Oh, well, clearly one morning, uh, Einstein rolled out of bed and he
Right.
came to understand all these new ways of understanding of how we think about the universe.
Yeah.
Of course, you don't understand that it's a process, and it's a process during most of the time where it is confusing, where people have no idea what's going on, where people have
Right.
differing opinions, where there are blind alleys and just things that nobody understands, and things that people are sometimes not even ready to understand,
Yeah.
because the science that we do is a human endeavor. And so, you're not ready to understand relativity, that for instance, that the idea that the passage of time is not absolute, until you come to understand that, well, that kind of thinking is connected with some of the moral relativism that was developed in the late 1800s. Isaac Newton was brilliant, probably the most brilliant scientist of all time, but he would never have been able to do the things that Einstein did, not because he wasn't capable of understanding the math or doing the science, but because he was framed by the time in which he lived.
Hmm.
The same reason that Einstein could help develop a lot of the basic ideas that go into quantum physics, and yet still never really be able to fully embrace those ideas, because that's not the place where he was from. It took the next generation of physicists who were able to then, okay, I can bring myself to see the world in a different way. And so, yeah, that you have to be engaged in the process to really understand the process. And in fact, it's one of the best things about undergraduate education in the sciences, is at a small college, is that we have the opportunity to engage students in our own work. It's really, it's at an R1 research university, right? The purpose of research is publications, bringing grant money,
Right.
edu- you know, providing education and experiences for graduate students. Undergrads are fourth or fifth on that list.
Yeah.
Um, Not here at North Central. Undergrads, that's who we serve. There are no, you know, my physics majors are all undergraduates. That my job is to make sure that I provide them with the background that they need, but also to give them the opportunity to engage in the doing of science. Just if because their education isn't complete until they've seen that and done it.
Yeah. The passion. I can hear the passion, and I can see the passion on your face. for what you do in the classroom. It's inspirational. It's one of the many reasons that you're such a highly regarded faculty member on this campus. Paul, what is Fermilab, and what is a Muon? And tell us about the research project.
So, Fermilab, the Fermi National Accelerator Laboratory, is a Department of Energy run facility that brings together users from all over the country, from all over the world. If I want to understand, it has a single mission. Its mission is to try to understand what are the fundamental constituents of matter and how do they interact with each other. So, once upon a time, everything was atoms. And then we learned that atoms had structure, that there were electrons, and that there was a nucleus, and that the nucleus was made up of things like protons and neutrons. And then we started poking at that and unraveling it, and over the span of about 100 years, we came to understand that nature is made up of a very short list, that all the stuff that we know about is a relatively short list of particles, things like electrons and the neutrino, the quarks, that make up all the stuff around us. And it turns out that there are heavier copies of those things, that there's a second generation. So the protons and neutrons are all made up of things called up and down quarks. And the electron is a fundamental particle. It also has a sibling, the electron neutrino, which is a ghost. It hardly interacts with matter. And that's the other thing, is that there are 4 known interactions that govern how those constituents talk to each other, how they tell each other to go away or come a little closer or stick together or whatever they're going to do. Gravity is the one we're most familiar with because it dominates our day-to-day life, but it turns out that has almost no role in fundamental physics as we understand it now, because it is an exceptionally weak force, and it only matters in the presence of enormous chunks of it, like if you happen to be hanging around near a planet, then you notice gravity. But the 3 forces that we deal with in what is called the standard model, our collective knowledge of these particles and interactions, we have the electromagnetic force. That's electricity, magnetism. It's all about how charged particles interact with each other. And it turns out that, for instance, if you want to understand chemistry, that's the entirety of electromagnetism, is all about how electrons stick together with nuclei to form atoms. But it turns out in the nucleus, there are additional forces at play. There is a strong nuclear force. When you take a bunch of protons and pack them really close together, they like charges repel. The electromagnetic force wants them to get away from each other, and yet they don't. They stick together in nuclei. The reason they do that is there is a force that we have cleverly called the strong nuclear force, because it is strong and because it acts in the nucleus. By the way, high energy physicists are disastrously bad at naming things. That's why we have stuff called quarks and gluons, and things that have the names that they do, because apparently nobody thought that this name might stick. Maybe you shouldn't choose something quite so silly, but it's what we've got.
Sure.
So we have the electromagnetic force, which is responsible for all the stuff we encounter in the day-to-day world. It tells us how atoms work. We have the strong nuclear force, which makes the constituents of the nucleus stick together, that those protons and neutrons can stick to each other. And really what's happening is that the particles inside of them, the quarks, are interacting with each other, and there's a little spillover, and it makes protons and neutrons stick together. And then there's the weak nuclear force, which is responsible for certain types of radioactive decay, and again, only plays out on the sort of the scale of the atomic nucleus. The nuclear forces don't show up in our day-to-day lives unless you happen to be working at a nuclear power plant or at a particle accelerator. And so those are the four fundamental forces that we know of. The two quarks and the electron and the electron neutrino. It turns out they have two sets of cousins. There are two additional families of particles. The two heavier quarks are charm and strange. There's the muon, which is the heavier version of the electron. The muon comes with its own neutrino. And then we have the heaviest family or generation still. We have the top and bottom quarks. And we have the tau particle and the tau neutrino. And the thing is that all of those heavier particles, they're unstable. We can produce them at an accelerator, but they don't hang around. They decay, they disintegrate into lighter particles. And so even something like the muon, which is almost identical to the electron, it's about 200 times heavier, but it's essentially, it does all the things that an electron can do, except because it's heavier, it can also decay. But the muon, and since you were asking about the muon,
yes,
muon is pretty unique in terms of the unstable subatomic particles because it lives a really long time. Now, a really long time is, you have to, it's not something you measure on your on a stopwatch. We're talking about 2 microseconds, right? 2 millionths of a second. But when some subatomic particles decay in 10 to the minus 24 seconds, 10 to the minus 6 is a very, very long time. And so some people call them quasi-stable. The point is, you can make muons and they will hang around long enough, especially if they are moving really fast, because then the special theory of relativity tells you that things that move, when you have things that are moving really fast, their clocks run slow. And so a muon can actually be produced and made to hang around for milliseconds, right? Thousands of times longer than it ought to hang around before disintegrating if it was just sitting there. And so that makes the muon fairly unique in terms of unstable particles that you can actually study, because you can make them hang around long enough to do things with them. And that's the essence of the reason why the muon G-2 experiment does what it does. And so this experiment is asking a pretty, in high energy physics, you tend to hear about things like the Large Hadron Collider and the experiments there, or in what was at the time the highest energy accelerator when I was in grad school was the Tevatron at Fermilab. And again, 2 big multi-purpose experiments with 600, 700, 800 collaborators who were looking at the data that these experiments collected and making all kinds of measurements, hundreds and hundreds of different measurements of what is the probability of this process happening, or how does this particular thing decay. And now at the Large Hadron Collider, we're talking about experiments that have thousands of collaborators who are producing vast numbers of papers on looking for new things, trying to figure out, again, to make more precise measurements of the properties of particles. And so it's a multi-purpose detector. It is an experiment which is trying to do many, many different things. What makes muon G-2 interesting is 2 things. One is it's relatively small, only a couple hundred collaborators, which seems big for most anybody else doing science, but in high energy physics, that's actually bite size by comparison. The other thing is we weren't trying to measure thousands of different things. We really had one purpose. There's a second purpose, but the fundamental purpose is to measure this magnetic property of a muon. So there is a This is true for macroscopic objects, and it is true for microscopic objects. If you have an object that has an electric charge and it is spinning, it will make itself into a little bar magnet, essentially, a magnetic dipole. So if I took a metal sphere and charged it up and spun it, it would generate a magnetic field around it. And I could take a compass and measure its magnetic field, and it would look a lot like the magnetic field lines that you've seen of a bar magnet. They're lines coming out of the North Pole, or actually, yeah, out of the North Pole and into the South Pole of the magnet, and they loop themselves around. And it turns out that even though a muon is not really a sphere, it's a point particle. The idea that it's spinning, we think of it classically as a little object spinning, but it isn't that. Whatever a muon is, it has this property, however, that it has electric charge and that it has what we call spin. It has this property, formally it's intrinsic angular momentum. But because of that, the muon has a magnetic dipole moment. It has it's a little bar magnet. And there's a trick you can do with a bar magnet. And that is, if you put that in a magnetic field, if the bar magnet points this way and the magnetic field points this way, the bar magnet will precess. It will spin. And the precession frequency, how rapidly it spins, depends on the strength of the external magnetic field and the strength of the bar magnet. And so this is a way that you can measure the magnetic dipole moment of the muon. And there's a calculation that in the standard model are collection of theories that tell you how to actually analyze all these fundamental processes, that tells you how to calculate what is the magnetic dipole moment in terms of the electric charge of the particle and its spin. And we know those things. And so you do that calculation, and there should be this thing, and that the proportionality between them is called the G factor. So that's the muon G factor that we're trying to measure. And at the most basic level, if you ask what that G factor should be, the original answer was, it should be exactly 2. But it's not 2. In fact, as soon as people did the first calculations, they said, well, wait a minute. It turns out that when we're talking about fundamental physics, when we're talking about understanding nature at the smallest scales, the vacuum is not empty. It actually contains a sea of particles which can pop into existence and then disappear. This is part of the uncertainty principle. You're essentially borrowing a little bit of energy from the vacuum. You can make these particles, they annihilate, matter and antimatter, and they vanish back into the vacuum. And it turns out that any particle in existence can participate in that game, even the ones we don't know about. And when they first started to add this correction in, because as soon as you allow for this process to happen, it changes the G factor, and it makes it a little different than 2. And in fact, it turns out to be an extraordinarily sensitive probe of what's going on in the quantum vacuum. So when we say the experiment is the muon G-2 experiment, we are trying to measure the G factor of the muon, but what we're interested in is the piece that isn't 2. The 2 is sort of the muon on its own in a classical vacuum, that it's just perfectly empty. But as soon as you let this sea of particles that are constantly popping into existence and then disappearing, well, the muon can interact with them through all the known forces and through all the known particles participate in this game. And you can start to calculate, well, what is the correction to 2? So you can calculate what G-2 is. And the thing that gets really interesting is if you can calculate that number to sufficient precision and you can measure that quantity to similar precision, you can test your assumptions about what is in the quantum vacuum. And in particular, if there's something you don't know about, well, you can't include it in your calculation, but nature doesn't care about your calculation. It can see, oh, well, this X particle is there, so let it play as part of this game. That will change the answer that nature gets versus what your theory gets. And so this was the big thing that people started, and this is an endeavor that, by the way, started all the way back in the late 1950s, that in the early days of the European High Energy Physics Laboratory, CERN, they figured out they were able to produce beams of, or at least produce muons. Usually you make beams of all kinds of stuff, and you can then muons are very good at traveling through materials, so you put a bunch of steel plating in the way. Usually you get that by cutting up something like an old battleship, but you put steel in the way, and it absorbs all the particles except the muons. And now you've got these muons, and you can learn something from this. And so the first attempted measurements of the muon G-2 were made all the way back in the late 1950s. So that's, several generations of physicists ago. And that is a process that has been refined as we get better at producing muons, as we get better at making this measurement and storing them. So for example, we in the most recent measurement, we store the muons in this big storage ring. You've seen pictures of it. And the reason for that is those muons have been accelerated up to 99.997% of the speed of light. They are really, really fast, almost as fast, almost, but not quite the speed of light. And because of that, even though those muons only typically live about 2 microseconds, in that ring, as they're racing around, they can go around for milliseconds. And that's enough time for them to go around many, many times. And the thing about the experiment is that it is designed to see that magnetic precession. And over time, some very clever accelerator physicists figured out, oh, actually, we can produce a beam of muons with all their magnetic dipole moments pointing in the same direction. And then you put them into the storage ring with a vertical magnetic field. And if you build the ring to be exactly the right size and it to exactly match the muon's momentum, then the natural precession, if G was equal to 2, that would happen at exactly the same rate as the muon goes around the ring. And so the magnetic dipole moment would always point in the same direction if G was equal to 2. But not equal to 2, so then it spins. And that is the piece that we can measure by watching those muons decay. Because it turns out that because those muons decay via the weak nuclear force, when they disintegrate, out comes an electron, and that electron is emitted preferentially in the direction of the muon's magnetic dipole moment. And so if that thing is rotating, then sometimes out comes the electron. Actually, we use positively charged muons, so it's a positron. But the point is, out comes this particle in one direction, and if it's in the same direction that the muon is traveling, it's more energetic. But the muon is precessing, which means the muon might be going that way, but its spin might be pointing the other way, and which means that when it decays, the electron is now ejected in the direction opposite of the motion. Well, if you have a ball and you're riding in a car down a straight road and you throw the ball in the direction that you're driving, then the person on the side of the road sees that ball going faster than you threw it. But if you throw the ball behind you, right, then they would see the ball going slower than you actually threw it. And so in the laboratory, what we see is that when when electrons are emitted from a muon decay, when the magnetic dipole moment is aligned with the direction of motion, the electrons are more energetic. And when they're opposite, they're less energetic. And so we measure those energies, and we can actually see the energy go up and down. That tells us how these guys are precessing. And that period of precession allows us to measure G, or rather it lets us measure G minus 2. And that measurement has progressed since the fundamental method for the measurement has been refined, but the measurement has gone from, we made a measurement back in the late 1950s. The first measurement was to a precision of a couple of percent. Our most recent measurement that was just published within the last year, 127 parts per billion. So about one tenth of a part per million, right? Really precise. And that actually lets us start to see and to test, is there some divergence between the experimental result and the theoretical prediction? Agreement is awesome because it says, hey, here's another place where your theory is actually, it's the standard model has picked up that name, the standard model, because it's been so good at predicting every result everything we've tried to measure. And yet we know that can't be the whole story. We have lots of reasons to believe that there's more physics out there, heavier particles, other things that we've not seen before. And we're striking out. We haven't found them, either because usually because our accelerators aren't powerful enough. And so what has happened in my field over the last couple of decades is that people have pivoted from let's smash things together harder to let's measure things with more precision to see if we can find places where there's a mismatch, even if it's at the 10th or 11th decimal place. The point is that if your experimental uncertainty is small enough and the precision of your calculation is good enough, that disagreement could be meaningful. And in fact, in the early 2000s, when this experiment was no longer at CERN, now being done at Brookhaven National Lab, they published a result which said there is about a 3 standard deviation difference between what we're measuring and what the theory is predicting. And that is a hint that, maybe there's something going on that you don't know about. And people started getting very excited. And that's why primary reason that the decision was made to, all right, let's continue doing this experiment. We got to do it at Fermilab because Fermilab can make a lot more muons, a lot better polarized, all these kinds of things. And we upgraded the experiment, upgraded a lot of the features of the detectors. And so now we have a much more precise measurement. Unfortunately, from the standpoint of wanting to discover something new, the theorists who are working on how do you do these calculations have also improved what they've done. And it turns out that difference vanished, that the two measurements are once again in agreement with each other, but to fantastic precision. And so it's a triumph of the standard model. It's a triumph of our ability to make measurements, to calculate things. But also we didn't get the big payoff, which is sometimes you'd like to break stuff. And no, so we didn't break physics.
You've had students involved in this project. What is the benefit for those students?
So the reason I stay involved in research, of course, is because it's interesting to me. But also, I have come to understand through my own experiences and in watching how students learn that you can't learn what it means to do science without doing science. Yeah. Students have to be involved in the process. And, laboratory experiments that we attach to courses have their use, but they're contrived, right? We know what's supposed to happen. And things go wrong sometimes, but there's a difference between that and really being out there of, I don't know what's going to happen. I tried something and I have no idea how to make sense of it. So students, any student of science, of the sciences, they're not going to have a complete education in the sciences until they actually do science, right? The book learning, the things that you do in instructional labs can only go so far. So students need that experience. And in terms of what students do, again, different disciplines do different things. In physics, I can't go down to the corner store and buy a particle detector, right?
Right.
Everything we build is a one-off. And yeah, sometimes we're building things using commercial electronic components and things like that. But a lot of instrumentation is built from scratch. And in fact, that's one of the things that any physicist will do. And it's true for me. It's true for Susan Kempinger. If you want to talk to the
Yes.
other physicist on campus,
Yep.
we build instrumentation because not some people, because they really enjoy building instrumentation. But as a physicist, I cannot make a measurement and learn something about nature until I have the instrument that I need. And in physics, because you're usually doing something new, you have to build that instrumentation yourself. And so it's given me the opportunity to have all kinds of things that students want to do, whether it's electronics for reading out. One of the projects I've been working on for more than the last 5 or 6 years is a magnetometer. It's a device that allows you to measure magnetic fields. And we, for G-2, have this task of we need to be able to measure the magnetic field in a certain region of one of the detectors that normally that they didn't think about instrumenting beforehand, and they realized, oh, you know what, this might be useful to have. And it wasn't the main measurement. It wasn't, it was a side project. It was a niche project. But the reality is, when you're a small college and you've got one faculty member who can give you, a quarter FT, full-time equivalent, and bring some students along in the summer, you have to pick and choose, your contributions carefully. You don't want to do, oh, give me the most important thing. Also, I can't work on it for 9 months. But finding things where, okay, here's a measurement that we need to make. How do we make it? Okay, I need to build an apparatus to measure magnetic fields, but I need to know where I am. So not only do I need a sensor that lets me measure magnetic field strength, I have to learn how to read out, because that's going to give me some electronic signals, and I have to learn how to make that into, do some signal processing and then get that onto a computer. At the same time, I have to know where those sensors are because I'm mapping something out. And so I had multiple years of students working on a project that ultimately all came together, but with lots of different pieces. I had one student, Daryl Watkins, who spent a lot of time building an actual aluminum fixture of, okay, I need drawings, and how is this thing going to bolt up to the actual vacuum apparatus of the main storage ring. And he got to learn by working with a machinist. Oh, things like when the machinist says, is that really what you want me to build? That's a warning, not a question.
Yeah.
But it's a learning process, and it's an incredibly important learning process.
Yeah.
Students working with, we're gonna make a map of this magnetic field. Do we want to do that manually? No, we would like to have some actuators and have motion control. Let the computer move the sensors to where they need to be and take the data and then move to the next piece. And so all of that got developed primarily by students. And I step in when I need to. I talk about, okay, big picture, what are we trying to do? But in the end, the students need to figure out, this is the task. And sometimes it's a very small, focused piece, and you got to understand how that fits into the bigger picture.
Yeah.
But extraordinarily important. It's the students come away from it. For instance, if they've been thinking about grad school, did you enjoy this? Did you enjoy this experience? If they say, no, I didn't, I hated this, don't go to grad school. You will be a miserable human being, right?
Yeah.
No, was this totally your thing? Great. This is the kind of thing you'll do in grad school after you get your coursework done. So, it's a learning process. It's also, I've had students who went on to be high school teachers. Well, why you didn't need to do research to be a high school teacher? No, but it does really help you talk about the experience of doing physics, right? Because for me, when I go and do research, I come back excited about doing physics, and that makes me a more energetic and animated professor in the classroom, right? So no matter what you're doing, if you're whatever you're going to do with that physics degree, right? Engagement in the doing of physics, right, can only help, right? It teaches you what the discipline is really about.
Paul, thank you very much. We've come to the end of the discussion, but we always end the podcast with your first memory of North Central and shout outs.
My first memory of North Central is I got picked up. I can't even remember who did it, but I got coming to campus for my interview and being picked up from my hotel and thinking like, this is Naperville. I lived here for 4 years. What are you going to, there's a college here. Wait, how did I not know there was a college here? And in my defense, when you're in grad school, you're blinders on, but just the shock of not just because clearly I applied, I read the website and things like that. So I knew there was a college, but actually seeing it and realizing like I had been 2 blocks from here and not realized that there was a college. So, okay. Sometimes you're meant to be where you're meant to be.
That's right.
What was this? Shout outs. First of all, to the good folks at Fermilab who, once upon a time, the idea that somebody who was sort of, well, you don't have any postdocs and you don't have any graduate students and you have to teach 9 months out of the year. How are you going to possibly contribute? There's a real understanding that, that the field is not overwhelmed with expertise and with manpower. And so you can't, that there is something to be gained on both sides. And of course, the value to the students, so I mean, just working with folks at Fermilab and in particular, a lot of the folks on the Muon G-2 experiment, and in particular, Dr. Mandy Kieberg, who is a longtime Fermilab employee, but has also been teaching and adjuncting at North Central for many years now, who said in the way that she often does, you should look at Muon G-2. It's doing some interesting things. As in, that was, again, the same way that my wife laughed at me when I told her he was a cool young professor. That was her gentle way of saying, hey, stupid, here's a really good idea, right? Yep. So this will be good for you and your students. And she was absolutely right. It was a fabulous experience working on that experiment. Yeah. And, just to all my colleagues here in the science building, I mean, this is just a great group of people to work with, and they all get it, right? They get like, this is why we do research. This is why we involve our students. This is why this is meaningful. And, there's a lot of that. And to my students, past and present, right? This is, sometimes you want to avoid talking about, it's a calling, right? It's been my privilege to be engaged and part of their experience, right? That for me, that's the thing that makes this job worth doing, right? That the joy of seeing them become, of going from befuddled freshmen to slightly less befuddled seniors.
Yeah. Our guest on episode 14 of 1861, the North Central College podcast, Dr. Paul Bloom. Paul, what a fascinating conversation today. Thank you. Thank you so much for sharing, and congratulations on your work at Fermilab, the Muon G-2 collaboration. What an incredible project. And thank you for giving us your time to explain that work. And thank you for all that you do for North Central students.
Thank you, Jim. And thank you for the opportunity to talk about what I do.
This is, again, episode 14 of 1861, the North Central College podcast. Our appreciation to Professor of Physics, Dr. Paul Bloom. And we thank our listeners for listening to this latest episode.